And that opened the field from something that was just basically a dream and a hope from when I started out to where we are today, a few decades later, where we now know there are more planets than stars in our galaxy.
Wow.
It's just an amazing result.
Why do planets so often come with company? Why does Earth carry a single moon while Jupiter hoards dozens? And why do some of those icy satellites hide oceans in the dark? Could worlds even farther away, planets we've only just begun to glimpse, also shelter their own companions? And if so, how would we ever find them, faint and fleeting in a galaxy of light? From ancient star maps to Einstein's lensing trick to billion-star surveys, the chase has always circled one question: are planets ever truly alone? Moons have always felt like quiet companions, scattered around the planets in strange and surprising ways. Ours is familiar, almost ordinary, yet even it hides a story of violence, born from a colossal collision in Earth's early youth. Farther out, Mars holds on to its misshapen scraps, Phobos and Deimos, while Jupiter and Saturn carry swarms of icy satellites, some cracked and leaking oceans beneath frozen skins. Europa and Enceladus in particular have become symbols of possibility, worlds where salty seas churn in the dark, warmed by tides, raising whispers of life in places where sunlight never reaches. Titan wraps itself in a thick orange haze. Triton spins backward around Neptune, and every orbiting rock, from Pluto's Charon to distant fragments circling asteroids, adds to the growing family. As of early 2025, astronomers have counted more than 891 of these companions, each one a small clue in the larger story of how planets and their worlds take shape. But the hunt doesn't end at the edge of our solar system. Beyond it, astronomers search for companions in the Milky Way using a trick of light and gravity called microlensing. It happens when a star drifts in front of another, and Einstein's theory plays out in real time. The nearer star bends the light of the one behind it, magnifying it for a fleeting moment. If that star hosts a planet, the planet's own gravity adds a sudden blip in the brightening, a sharp little deviation that can last just hours, or even minutes, if the planet is as small as Mars. These signals are rare and fragile, demanding telescopes that can measure every flicker with impossible patience. Unlike methods that need bright nearby stars, microlensing reveals cold, distant worlds and even lonely wanderers drifting free of any sun. To see what treasures might be waiting, scientists built simulations like XELS, feeding in models of the galaxy, star fields, and entire catalogues of possible planets. Then they let the math play out, testing which worlds might leave fingerprints strong enough to catch. The numbers came back generous. Hundreds of new planets, perhaps, filling in gaps that other methods miss. Together, the two stories, the moons close to home and the planets hidden across the galaxy, fold into one. Companions come in many forms, from lopsided rocks clinging to Mars to ocean-bearing worlds circling Jupiter, to icy Earth mass strays drifting between the stars. All of them remind us that planets, it seems, are rarely alone. Astrometry has always been about knowing exactly where things are in the sky and how they move. Long before it became a science of billion-star surveys, it was the quiet craft of measuring and remeasuring, building catalogues that became the backbone of astronomy itself. Timekeeping, navigation, even our understanding of gravity and motion all grew out of these simple but stubborn measurements of positions on a celestial map. It goes back to Hipparchus in 190 BC, who compared earlier star charts and realized Earth itself was slowly wobbling, precessing across the heavens. He also gave us the brightness scale still in use today. Ptolemy expanded the list in the Almagest, cataloging over 1,000 stars. Then, through the Islamic Golden Age, scholars like Al-Sufi, Ibn Yunus, and Ulugh Beg sharpened these records with remarkable precision, laying the groundwork for the Renaissance. By the 16th century, Tycho Brahe was pushing accuracy to a new level with his great mural instruments, while Taqi al-Din added mechanical clocks to track right ascension more carefully. The telescope shifted everything again. James Bradley caught the faint wiggle of Earth's axis, discovering both the aberration of light and nutation, while Friedrich Bessel broke open the sky's scale entirely by measuring stellar parallax for the first time, proving stars were not just pinpricks, but unimaginably far away. For centuries, only a handful of parallaxes were nailed down, barely 60 by the late 19th century. But photography changed that. Astrographs and glass plates allowed astronomers to freeze the sky, measure it again and again, and dream bigger. Even the failed Carte du Ciel project, which aimed to chart the whole sky, confirmed photography was the new language of astrometry. Later, charge-coupled devices shrank the uncertainties to milliarc seconds, turning precision into something achievable by more than just elite observatories. Then came the leap to space. Hipparcos, launched by ESA in 1989, rose above Earth's atmosphere and gave us astrometry unblurred. It pinned down the positions, motions, and parallaxes of over 118,000 stars with a clarity never seen before. Its catalogue spilled into every corner of stellar astronomy, from binaries to variable stars. 2 decades later, Gaia took the baton and expanded the vision to staggering scale. Since 2013, it has been sweeping the sky, measuring nearly 2 billion stars with micro-arcsecond precision. Each star drifts across its detectors about a dozen times a year, each crossing sharpening the map. The errors vary, from about 10 micro-arcseconds for bright stars to just under 600 for the faintest. But the reach is unprecedented. Gaia even stretches into photometry and spectroscopy, gathering colors, motions, and chemical fingerprints. It can untangle double stars, trace asteroids, and follow variable stars across the galaxy. With Gaia, astrometry has become the skeleton key of modern astrophysics. It anchors the cosmic distance ladder through parallax. It reveals the subtle wobbles of stars tugged by exoplanets. It traces pulsars flying away from supernovae, helping us test how explosions unfold. It lets us map dark matter by watching how stars move through the Milky Way's invisible mass. Even planetary defense leans on these measurements, as near-Earth objects are tracked to safeguard the planet. Some of the solar system's most intriguing worlds, like Quaoar and Sedna, were first uncovered this way. Tiny shifts in the sky betraying vast bodies on the edge of sunlight. From Hipparchus's first lists, scratched into parchment, to Gaia's billion-star atlas, astrometry has transformed from painstaking cataloging into micro-arcsecond storytelling. What began as a way to chart the heavens has become a way to rewrite our place in them. Astronomers peering through the James Webb Space Telescope may have stumbled on something extraordinary just 4 light-years away, a giant planet circling Alpha Centauri.
Using NASA's James Webb Telescope, say that they have found the strongest evidence yet of a giant planet orbiting Alpha Centauri A. That's part of the star system closest to the sun. If confirmed, it would be the closest planet in the habitable zone of a sun-like star. However, scientists do say it would not support life.
The system has always held a kind of magnetism, sitting right next door with its 2 sun-like stars and the faint red dwarf Proxima, already known to harbor 3 planets of its own. Yet for decades, the brighter pair resisted confirmation, their glare, closeness, and constant motion making it nearly impossible to spot any companions. Webb changed that. Using its mid-infrared instrument, scientists picked out a dim object more than 10,000 times fainter than Alpha Centauri A, hanging at a distance comparable to twice Earth's orbit from the Sun. If it is real, it's likely a gas giant about the mass of Saturn, looping around its star in a stretched elliptical path. It wouldn't be a world for life, but it would be the closest giant planet ever directly imaged around a sun-like star. Exomoons would not just be another entry in the catalogue of strange worlds, they would crack open a whole new frontier. A large rocky moon with an atmosphere, locked in orbit around a giant planet in the habitable zone, could be as compelling a candidate for life as any Earth-like planet. Even far from starlight, tides alone could keep oceans warm and surfaces geologically alive. Their existence would force us to rethink how moons form, whether they're captured wanderers, children of a circumplanetary disk, or the leftovers of violent migration. And they would remind us that a single system doesn't just host one world, it can host several, each reshaping the orbits, the climates, and the long-term stability of its neighbors. The first exomoon won't be a novelty. It will redraw the map of where life could hide.
So if some fraction of those gaseous planets have themselves a moon system, there may very well be more habitable moons than there are planets in the universe.
To find them, astronomers will need to sharpen the very tools they already use. Transit-like curves will have to be combed for timing offsets and odd asymmetries, subtle traces of a small companion tugging at a planet. Microlensing will be pushed to catch not just planets, but their moons in fleeting brightening events. Direct imaging will have to stretch contrast and resolution to tease out a faint speck buried in a star's glare. Every improvement demanded by exomoons will spill over into exoplanets, free-floating worlds, and whatever else lurks between the stars. The chase itself becomes an engine of discovery. We won't send phone-on counters to exomoons, but the lesson carries. The same obsession with noise budgets, correlations, and back action must anchor astronomy. When the claim is life, the error bars need to be quantum sharp. It all comes together as a kind of playbook. Define the targets. Large, potentially atmosphered moons heated by tides. Build the techniques. Refine timing, sharper imaging, more daring microlensing. Borrow the discipline of quantum metrology, measurements that don't flinch under scrutiny, and interpret cautiously, biosignatures as a suite, never a single flag. This isn't just about adding new dots to the sky, it's about making sure every dot we circle as a world stands up to the weight of what we're claiming. That discipline becomes the foundation of a playbook. Define the targets, sharpen the tools, and commit to testing every claim as if the stakes were everything. The first true exomoon will change things overnight.
One of the solutions to the Fermi paradox is lack of moon. In other words, life on Earth is somewhat dependent on the presence of a moon. And if it turns out that exomoons are rare, that could be a solution to the paradox.
Astronomers will rush to count them, to classify their sizes and atmospheres, to understand how they shift the balance of planetary systems. Models of planet formation will be rewritten, no longer able to ignore these secondary worlds. Life detection strategies will expand instantly, no longer limited to planets alone. Missions will be reshaped around the need for deeper contrast, better starlight suppression, and broader wavelength reach, because moons are dim, cool, and hard to tease out of the glare.